Hello, everyone, and welcome to Using the Salt Balance to Irrigate More Efficiently. Today's presentation will be about 30 minutes, followed by about 10 minutes of Q&A with our presenter, Dr. Gaylon Campbell, whom I will introduce in just a moment. But before we start, we've got a couple of housekeeping items. First, we want this webinar to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll be keeping track of these for the Q&A session toward the end. Second, if you want us to go back or repeat something you missed, don't worry. We will be sending around a recording of the webinar via email within the next 3 to 5 business days. All right, with all of that out of the way, let's get started. Today, we'll hear from Meter Principal Engineer, Dr. Gaylon Campbell, who will discuss how to improve irrigated crop production through the measurement and management of the water and salt balance. Gaylon has been a research scientist and engineer at Meter for over 25 years, following nearly 30 years on the faculty at Washington State University. His first experience with environmental measurement came in the lab of Sterling Taylor at Utah State University, making water potential measurements to understand plant water status. He's one of the world's foremost authorities on physical measurements in the soil-plant atmosphere continuum. His book, An Introduction to Environmental Biophysics, written with Dr. John Norman, provides a critical foundation for anyone interested in understanding the physics of the natural world. He has written 3 books, over 100 refereed journal articles and book chapters, and has many patents. So without further ado, I'll hand it over to Gaylon to get us started.
Okay, thank you, and welcome to today's seminar. We'll be talking about water and salt balances in irrigated agriculture. We'll also talk about how to measure them and what to do with the information to do a better job of irrigated crop production. Now, there's no shortage of news these days about climate change, the strain on our water resources, and concerns about having enough water to produce our food. Along with population growth, decreasing supplies of fresh water are a major concern. Of all of the water on Earth, only about 1% of it is fresh water, and only half of that is available for use. Of that fresh water, 70% of it is used in agriculture. Takes a lot of water to produce our food, 2,000 to 5,000 liters per person per day, we're told. Now, scientists and makers of scientific instruments, is there anything that we can do to help this situation? Well, I think there is. Even where supplies of fresh water are short, a lot of water is wasted. The way to start eliminating waste is to measure it. We can help supply the tools that will quantify water use and waste. Water use efficiency is the number of grams of dry matter that we produce per kilogram of water that the crop uses. We know how to measure dry matter production and water use, and we know the factors that determine both of those. So we're in a good position to both measure it and to improve it. Finally, irrigation has been practiced for thousands of years. In some cases, as in Egypt along the Nile River, it's been practiced in a sustainable way. But in most places where irrigation has gone on for a long time, there are problems with salt. We know the practices that are needed for sustainable irrigated agriculture, and we know the measurements that need to be made to assure that those practices are followed. Now, Dr. Richard Stirzaker, a CSIRO soil physicist in Australia, published a book in 2010, Out of the Scientist's Garden. He calls it a story of water and food. In it, he talks about a Goldilocks principle and relates it to his own career path in water management research. He started out focusing on instruments for monitoring the root's own water content for irrigated management. Now, correct measurements of soil water content, and especially soil water potential, are important for proper day-to-day irrigation management, but they don't give much insight into sustainability. They're too fast. He then studied salt in groundwater and rivers Again, this is important information for an irrigation project, but it's too slow for management decisions. By the time you see those responses, the battle's already been lost. Dr. Stirzaker finally started focusing on salts in the root zone, and this was just right to provide the information needed for proper sustainable management of irrigation. So today we'll talk about how to make those measurements and make use of them. Now, the first measurements we need to address these problems relate to the water budget. We need to know the water inputs, losses, and the change in water storage in the soil. For the inputs, the rain gauge on the Atmos 41 or 41W microenvironment monitor per meter will measure precipitation. We'll also measure irrigation from sprinklers if you put it under the sprinklers. For the evapotranspiration, the Atmos 41 also measures solar radiation, temperature, vapor pressure, and wind, from which Centra Cloud, the cloud service connected, computes reference evapotranspiration. Using reference ET and an appropriate crop coefficient, you can calculate the evaporative losses. Drainage is another loss, and later in the seminar we'll talk about how to measure drainage. For the storage, the Terros 12 soil moisture, electrical conductivity, and temperature sensor will monitor changes in soil water content. So the sensors shown here will go a long way toward monitoring the terms in the water budget. The salt budget also consists of inputs, losses, and storage. The main input in it is the irrigation water. Salts are in all irrigation water. When we irrigate, those salts enter the soil. The water leaves the soil mostly as evapotranspiration. The water can evaporate, but the salts don't, so they stay in the soil. Now, if you take the rain funnel off of the meter's Atmos 41W microenvironment monitor and look in the bottom of the basin below the tipping spoon, you'll see two screws. They're shown here by the arrows in the left-hand figure. Purpose of those screws is to measure the salt in the water the rain gauge is intercepting to help us measure that component of the salt balance. There are other important sources of salts in the soil. We apply chemical fertilizers to crops. Crops take up some, hopefully most, of that, but some usually stays. Groundwater also contains salts. The water table is sufficiently close to the surface. Evaporation will bring the salts to the surface. Over-irrigation brings the water table to the surface, and it's therefore often the main cause of salinization of irrigation projects. Drainage systems can drop the water table and mitigate this problem, but it's better and cheaper probably to avoid the excess irrigation in the first place. Now, we could quantify the salt in the soil in a number of different ways. We could do it by stating its concentration, but typically we describe it in terms of the electrical conductivity. This graph that was originally published by R.B. Campbell and Associates in 1949 shows that the electrical conductivity and osmotic potential of the soil solution are linearly related, with a slope of about 35 kilopascals per decisiemens per meter. And that's a useful number to use in understanding how salts stress a crop. The osmotic potential and concentration are also linearly related. Now, why do we care if the salts build up in the soil? Since plants take up water through membranes, that are permeable to water but not to salt, increasing the salt concentration in the soil solution decreases water availability to the plant and causes water stress, just like a dry soil would. This reduces production and the yield from the crop. Soil salinity in crop production has been studied extensively over the past 100 years or so. Here are some of the results of those studies. This shows corn grain yield as a function of soil solution or pore water electrical conductivity. The yield isn't affected until the electrical conductivity gets up to about 4 decisiemens per meter. That's an osmotic potential of around minus 150 kilopascals, but then the yield starts to fall pretty rapidly with increasing EC. Now, crop species differ in their sensitivity to osmotic stress. Here's a list of crops organized according to the sensitivity. To those experienced in irrigated agriculture, a list like this isn't any surprise. Probably you know where the salty soils are. You also know what will and won't grow there. Graphs similar to the one we showed earlier for corn can be created for each of the 4 groups of crops. And we get a graph like this. So for a particular crop and a particular soil salinity, one can enter the graph and know how that graph will perform under a given salinity regime. Now, I've been talking about electrical conductivity without being very specific about what I mean by that term. I want to get a lot more specific now. We'll refer to 3 kinds of electrical conductivity, and it matters a lot which one is which. So it's important that you understand which is which. The first is the bulk electrical conductivity, EC sub B. If I stick one of our Taros 12 sensors in the soil and measure the electrical conductivity of the soil, that measurement will be the bulk electrical conductivity of that soil. Now, that number doesn't mean much by itself. It's not very useful, but it, along with other data, can be converted into much more useful numbers. If I were to somehow squeeze or suck the water out of the soil and measure the electrical conductivity of that water, that would be the pore water or the soil solution electrical conductivity. We use EC sub W for that. That's the EC the plant sees, and it is the osmotic potential of that water that determines how stressed the plant will be. The final one is called saturation extract EC or EC sub E. You get it by saturating a soil sample with distilled water, squeezing some of that water out of the soil and measuring the electrical conductivity of the water. When someone talks about the electrical conductivity of a soil, that usually is the number they mean. That value has been used to classify soils for years and years. It may seem like a completely arbitrary way to get a number, but it turns out to be a direct measure of the salt content of the soil. Now, for crop production, the pore water electrical conductivity is the important one, since that's the one that the plant senses. One way to measure that is to suck some water out of the soil with a suction sampler and measure its electrical conductivity. And that was the method used to get the data in the corn salinity response graph that we showed earlier. Modern sensors allow us to get it a lot more easily and to get a continuous record of it. The Taros 12 measures the bulk electrical conductivity of the soil and its dielectric constant. The Hilthorst equation says that the ratio of pore water EC to bulk EC should be the same as the ratio of water dielectric to the increase in the bulk dielectric from adding water to the porous material. So we can use that equation and the bulk EC and dielectric measurements to compute a pore water EC. Now that's powerful, since now we can know the EC the plant sees, and therefore the extent of the salt influence on the crop throughout the growing season. Now at this point we should have a good understanding of the principles for managing salt and water in irrigated agriculture. But how do we apply them? You can't see the salt in the irrigation water. By the time it's concentrated enough to taste, it's too salty to be used for irrigation. You won't know what the state of salt is in the soil until the crops fail, and then it's too late. You need a way to measure the salt. Here are some excellent tools to help with that. The ES2 measures the electrical conductivity of irrigation water. The Taros 12 measures the water content and bulk electrical conductivity of soil. Those are plugged into the ZL6 data logger, and that connects to Zentra Cloud through a cellular connection. The data flow to the cloud through the cellular connection, and the computations are made in Zentra Cloud to give you pore water electrical conductivity and the electrical conductivity of the irrigation water. Now with tools like this, we can continuously know the electrical conductivity of the irrigation water, the pore water EC in the root zone so that we can avoid stressing the crop, and the pore water EC below the root zone, which will help us determine the rate of drainage. Before we go on, let's say just a few words about leaching fraction. It's the ratio of the amount of water draining out the bottom of the soil profile to the amount of water that we have applied to the soil. If we go through the calculations, you'll see that that definition is equivalent to the ratio of the electrical conductivity of the irrigation water to the electrical conductivity of the drainage water. But the electrical conductivity of the drainage water is the pore water EC. This calculation is normally used to compute the amount of water we need to apply in excess of crop requirements to maintain some desired electrical conductivity in the root zone. So for example, if we were applying 0.6 decisiemens per meter irrigation water and wanted to maintain a pore water EC of 3 decisiemens per meter, we would need to apply 20% more water than the crop uses. But we could turn this around and apply it in the other way. We could measure the electrical conductivity of the irrigation and of the soil below the root zone and know how much water we're losing to deep drainage. And this gives us some insight into why Dr. Stirzaker said knowing the EC in and below the root zone is the Goldilocks measurement. So here's a scenario. The Taros 12 measures water content and bulk electrical conductivity, which goes to the ZL6, then Zentra Cloud, and is converted to pore water EC. The value at the bottom of the root zone is Stirzaker's Goldilocks measurement. We can use it for crop suitability, crop loss calculations, or to estimate drainage losses. For example, let's say that the electrical conductivity, the ECW value was 5 decisiemens per meter, and we wanted to grow strawberries. Strawberries are a sensitive crop, so going up from 5 in the graph, our value in the soil, we see that the salt would likely reduce our yields by about 18%. Now then, that information would be useful in determining whether that's the right crop to choose, and if so, what kind of yield reductions we could expect from the salt in the soil, or what adjustments we should make in that pore water EC. On previous seminars, I've shown data obtained from experiments conducted, a collaboration of meter scientists with faculty at Brigham Young University and a very progressive farmer in southern Idaho. These data are from that same farm. They're computed electrical conductivity values under irrigated wheat. 3 depths are shown, 15, 45, and 65 centimeters. Now remember, this is a picture of the salt concentration in the soil water at the level of the measurement. The shallowest level is in blue. A couple of spikes are shown, probably from nutrient additions from fertigation. The middle depth shows a couple of bumps, probably from those fertigation, but a general decrease that's likely from the plant uptake of the nutrients. At the lowest level, we see a slight increase, probably from the downward movement of salts from the upper levels in the soil. The irrigation water had an electrical conductivity of 1.1 decisiemens per meter. If that were the only source of water, the leaching fraction would be around 25%. But a proper analysis need to include precipitation, which has almost no salt in it. If that applied water were half irrigation and half precipitation, the leaching fraction would be half that. Now, this record's too short to make any grand predictions about general trends and sustainability, but if we had a record 10 or 20 times this long, we'd have a pretty good idea of how sustainable our practices are and what changes are required to improve sustainability. Now here's another scenario. The DARIS-12 measures water content in bulk EC, which goes to the ZL6 and Zentra cloud and is converted to pore water EC. At the same time, we measure the EC of the irrigation water using an ES2. We rearrange the leaching fraction equation to give depth of drainage, and then from that amount of water applied and the 2 measured electrical conductivity values, we can compute the drainage rate. If a significant fraction of the water that's applied is rain, the irrigation EC needs to be adjusted for that. If a significant amount of the added salt is fertilizer, we need to make that adjustment too, but those adjustments are fairly straightforward. Hope it's clear now from our discussion that the only way we can correctly manage irrigation is to know the salt content of the irrigation water and the water and salt content of the soil. And the only way to obtain that knowledge is to make measurements. I hope you also see why Dr. Stirzaker considers the pore water EC as the just right measurement for managing irrigation, since its value depends on the outcome of both the water and the salt budget. Finally, I hope I have given you some insight into the tools you can use to make the irrigation decisions. Thank you.
Okay. Thank you, Gaylon. So we'd like to use about the next 10 minutes or so to take some questions from the audience. Thank you to everybody who's sent in questions already. We've got a few that have come in already. And there's still plenty of time to submit questions if you'd like. We'll get to as many as we can before we finish. If we don't get to yours before we finish with this live webinar, we do have them recorded, and somebody from our meter and environment team will be able to get back to you via email to answer your question directly. Let's see. Our first question here is asking, what role do you see biochar playing in water balancing?
Don't have much experience with biochar, so it's a hard question for me to answer. I'm not aware that it changes either the salt or the water budget very markedly, but I could well be wrong about that.
Do you know, I'm trying to think of other soil amendments that there might be that might affect either the water or salt balance.
Yeah, those kinds of things certainly affect nutrient availability and nutrient storage in the soil, those kinds of things. So they have an effect on those parts, but not so directly, at least to my knowledge, on what we're talking about today.
Next question here. They are asking, how reliable is bulk EC when compared to pore water EC?
Well, as I said, bulk EC by itself is a pretty useless number. It's a measure it's a measure that's influenced by temperature, by water content, by salt content, but it doesn't sort any of that out for you. And so it really is, what we need is a number that reflects what the plant is seeing, and that the bulk EC doesn't tell you anything useful about that without being converted to a pore water EC.
Next question is asking, what about organic matter, and how does that influence the water balance?
Again, organic matter has a tremendous effect on a lot of factors related to soil health. And so in terms of infiltration rate, whether the water actually goes into the soil that we apply to the surface, that's strongly affected by organic matter. The calculations I've been showing today, we assume that whatever water we apply goes into the soil, and that's not always a good assumption. So in the overall picture, the organic matter plays a big role, but that's not something that I tried to address today.
Let's do this question here. Can we use salt ballot measurements to help us quantify the potential for groundwater recharge?
Sure. The groundwater recharge, all of the recharge that there is comes from the drainage. There are various ways of trying to quantify drainage. We could try to do it through a water balance, knowing how much we are putting in and how much we're evaporating, but there are big uncertainties there. And so the method that we talked about here today, I think, is one of the most reliable ways of estimating drainage, and therefore estimating recharge. In other words, using the salt and water balances.
Can the application of soil proximity sensors effectively measure soil water content and electrical conductivity in real time, providing reliable data for optimizing irrigation and soil management practices? So just being able to use soil proximity sensors, can those effectively measure soil water content and electrical conductivity in real time?
I'm not sure of what a soil proximity sensor is. Certainly electromagnetic sensors, non-contact sensors, I assume that's what's being talked about. There's a lot of work going on to try to use those. From my experience, we still have quite a ways to go before those will give us precise enough measurements to use for water balance estimates.
Within dryland farming, can we use these tools when we're dealing with the water balance to then be able to estimate the amount of rainfall needed in order to have a certain yield within the crop?
Again, this is focused on. We could use these kind of tools to know whether there was an excess of rain. In other words, whether recharge was occurring, as long as we had a salt tracer there to monitor that with. But I'd probably use other ways of knowing whether the rainfall was adequate for producing the crop that the rest of the environment was capable of producing.
I guess along with that, could you say a little more about including rain and fertilizer and other things into the balance?
That if we were doing those calculations for recharge, let's say, or for drainage, we need to include all of the water and all of the salt. And part of the salt can be the salt in the irrigation water, but part could also be excess fertilizer that was applied. And we'd have to know how much excess there was. We'd need to know, and if we know what the biomass was that was produced, we know the nutrient concentration in the biomass, we could compute the amount of nutrient that was taken up. We'd also need to know how much fertilizer had been applied, and that would tell us, give us an estimate of the excess there. And then if we know the amount of rain and the amount of irrigation, then we can make adjustments to our calculations there.
All right. This next individual is asking, then, can we use these sensors? And I think he's meaning the ES2 to measure EC in reservoirs.
Sure. Well, all of these will measure. The ES2 that we talked about, it'd be the one that would be best for that. Could use it for any irrigation water source or any water source to determine the salt concentration.
We're coming close to the end of our time. I think we'll do one or two more. This one individual is asking, can we use the saltwater balance to know when to irrigate without taking a crop to stress beyond a certain threshold?
If salt stress is the main concern, then we need to know how much. If our salt concentrations are getting high enough to stress the crop, then we need to apply enough water to leach the salt out. And we have a continuous record of the salt concentration. We know how much salt it takes to stress the crop and lose production. And so it's pretty straightforward to know how to make irrigation decisions on that. Now, if the matrix stress is also a concern, then we also would need to monitor that. With the Terros 12 sensor, we'd have a water content measurement, and so we could use that.
I think this is going to be our last question for today. Thank you again, everybody, for submitting your questions. If we did not get to them, and we have several that we did not get to, again, one of our experts from our meter environment team will be able to get back to you and answer your question directly. So this last question here, and Gaylon, you talked about using, for instance, the Terros 12 in measuring water content and EC. This individual is asking, when using matrix potential sensors for irrigation management in salt-affected soils, can one account for the osmotic effect when determining the irrigation trigger point?
Not without a measure of the electrical, the pore water EC. You'd need, the matrix potential sensor will give you the matrix stress, but not the osmotic stress. You need a pore water EC for that.
Okay. So yeah, team up our water potential sensors with water content sensors. They work great together. All right, that is going to be it. That wraps it up for us today. Thank you again for joining us. We hope you enjoyed this discussion. Thank you again, everybody, for such great questions. Also, please consider answering the short survey that will appear after the webinar is finished, just to let us know what types of webinars you'd like to see in the future. And for more information on what you've seen today, please visit us at metergroup.com. Finally, look for a recording of today's presentation in your email and stay tuned for future meter webinars. Thanks again, stay safe, and have a great day.